SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Good afternoon, students. Today I'll be talking about the topic ordinary differential equations. The course code is MAT 206, that is from SYBSE semester 4. When we talk about ordinary differential equations, there are certain topics we need to cover first. What I would be covering today is introduction to ordinary differential equations, initial value problem, one-step methods, of which I'll be discussing Taylor series method, Euler method, Runge-Kutta second order, Runge-Kutta fourth order methods, and also I shall introduce you to certain practical applications of ordinary differential equations. In order to understand or solve an ordinary differential equation, we should first understand what are differential equations. An equation that contains dependent and independent variables and also has one or more derivatives of the dependent variables is called a differential equations. We already know that when we talk about dependent and independent variables, let us assume that y is a function that is dependent on x. So x is the independent variable and y is the dependent variable. An equation that has the derivatives of these independent and dependent variables is called a differential equation. Now these derivatives can be ordinary or partial derivatives. Since the topic of discussion today is ordinary differential equations, we would first have a look at what is an ordinary differential equation. If y equal to fx is the function that we have, then dy by dx is called the ordinary derivative of the function y. So any equation involving only ordinary derivatives is called ordinary differential equations, or in short we call it ODE. For example, dy by dx is equal to x upon y, or dy by dx is equal to x square plus y square. Now the function is y equal to f of x, and dy, that is a derivative of y with reference or with respect to x, is dy by dx. Any equation that contains this ordinary derivative dy by dx is called an ordinary differential equation. When we talk about ordinary differential equations, there are two aspects that we need to know and understand. The first is called the order of the ordinary differential equations. The order of the differential equation is the order of the highest order derivative in the equation. Let us take an example to understand this better. We have an ordinary differential equation, d2y by dx square is minus dy by dx plus 3 is equal to 0. In this case, the first term is a derivative, the second term is also a derivative. When we talk about the first term, d2y upon dx square, it is the second order derivative of the function y equal to fx. Let us talk about the second term in this equation, which is dy by dx. This is the first order derivative of the function y equal to fx. Now there are two derivatives in this equation, but the order of the differential equation is the one with the highest order derivative. So when we talk about this equation d2y upon dx square, it is the second order derivative, and dy by dx is the first order derivative, and hence this ordinary differential equation is said to have an order 2, and hence we would say it is a second order ordinary differential equation. Let us take another example. d3y by dx cube plus dy by dx plus x square minus y equal to 0. Again, in this equation, there are two terms that denote the derivatives. The first term, d3y by dx square, is the third order derivative. The second term, dy by dx, is a first order derivative. Now, we said the order of the differential equation is the highest order of the derivative that the ordinary differential equation contains. In this case, the highest order is order 3, and hence this ordinary differential equation is said to be having order 3, or we say it is a third order ordinary differential equation. Another aspect of ordinary differential equation that we need to know is the degree of the ordinary differential equation. Now, the degree of the ordinary differential equation is the degree of the highest order of derivative that the ordinary differential equation contains. Let us understand this through an example. We have an equation, an ordinary differential equation of the form d3y by dx cube square plus 2 dy by dx minus y is equal to 0. Now, what is the order of the ordinary differential equation? The order is the highest order, and the highest order derivative in this ordinary differential equation is 3, and hence the order of the ordinary differential equation is said to be 3. And what is the degree of the highest order? The degree of the highest order derivative is 2, because it is d3y by dx cube whole square. So, since the degree is 2, that relates to the higher order derivative, the degree of this ordinary differential equation is said to be of degree 2. So, this equation d3y by dx cube square plus 2 dy by dx minus y equal to 0 is said to have an order 3 but degree 2. Let us reiterate with another example. dy by dx square is equal to x square minus y square. Now, this ordinary differential equation has got just one derivative, and the order is 1 because it is dy by dx. So, the maximum or the highest order of this ODE is 1. And what is the degree of the highest order? Is 2. And hence the degree of the ordinary differential equation is said to be 2. So, dy by dx whole square equal to x square minus y square is said to be a first order ordinary differential equation having degree 2. Let us also introduce ourselves to the concept of initial value problem. Whenever we need to find the solutions of ordinary differential equations, we first need to identify the category to which this particular problem belongs to. Basically, there are two categories. The first is initial value problem and the second is boundary value problem. Since the course covers only initial value problem solution methods, we shall be talking about initial value problems today. So let us first define what is an initial value problem. If we have a differential equation, given the condition y of x1 is equal to y1 at the initial point. Now, what do we understand by an initial point? We are supposed to find out the solution of the ordinary differential equations within an interval, say a to b. So, a is said to be the initial point of the interval and b is said to be the final point. If we have been given the value of the differential equation at the initial point, say x1, y1, that is y of x1 equal to y1 is known to us, then such a problem is called an initial value problem, and in short we call it IVP. The initial value problem of an ordinary differential equation takes the form y dash x is equal to f of x y of x, where y of x1 is equal to y1, that is the value of the equation at the initial point x1 is known to us, that is for the first point x1 the value of y1 is known to us. then such a problem is said to be an initial value problem. There are two approaches to solve ordinary differential equations, and particularly the initial value problems. And the two approaches are one-step methods and multi-step methods. Again, our syllabus comprises of one-step methods, and hence I will be talking to you about several one-step methods available for solving the ordinary differential equation. Now, what are one-step methods? Because we need to actually understand both the approaches before we actually go into finding the solution of the ODEs. One-step methods are methods that use the information from only one preceding point in order to estimate the consecutive value of yi plus 1. That is, since it is an initial value problem, we have been given the value of x1 and y1. That is, y of x1 is equal to y1 is known to us. Now, since we know the value of y1, one-step methods help us to find out the value of y2 using the value of y1. It helps us to find out the value of y3 using the preceding value y2. y4 can be found out using the value y3. That is, these category of methods or these approaches, this approach of solving the problems uses only one preceding value in order to compute the next consecutive value of the ordinary differential equations. Whereas the multi-step methods use information from two or more previous steps to estimate the value of yi plus 1. Here we can say that though we have the value of the initial point, that is, we know the value of y1 at x equal to x1, but in order to find out the value of y2, we may not be able to find the value directly using one of the multi-step methods. In order to use a multi-step method, we may have to use one-step methods to compute the multiple preceding values. For example, if we have to use 4 preceding values to find out the value of the subsequent yi plus 1, in that case, we need to have the value of yi minus 1, yi minus 2 and yi minus 3. We need 4 preceding values. But what are we given? We are only given the initial value. That is, yi minus 3 is known to us because it is an initial value problem. Using any of the one-step methods that we shall be talking about now, we can compute the subsequent, that is the second, third and the fourth value of yi's. Then with these 4 values, we would be deploying them in the multi-step methods in order to find out the value of yi plus 1. And that is why these methods, since they use more than one previous values, these methods are called multi-step methods. In the course of the discussion, we shall be talking about one-step methods alone. And of the one-step methods, let us introduce ourselves to the first and the most simplest form of the method, which is called the Taylor series method. Given a differential equation dy by dx equal to f of xy with an initial condition that y is equal to y1 at x equal to x1. Now, if the solution curve is expanded in Taylor series around x equal to x1, then we get y of x is equal to y of x1 plus x minus x1, y dash x1, that is the first order derivative of y at x1, plus x minus x1 square upon 2 factorial into second order derivative of y at x1, plus x minus x1 cube upon 3 factorial into third order derivative of y at x1, so on and so forth. Here y dash x, y double dash x, etc. are the first, second order derivatives and so on. Now, this is a very familiar equation. This is the Taylor series expansion. We shall use this Taylor series expansion in order to compute the value of an ordinary differential equation. Let us learn this through an example. The example is thus: use Taylor series to find y of 0.1 correct up to 4 decimal places if y of x satisfies y dash is equal to x minus y square and y of 0 is equal to 1. Let me make the example clear to you. Y of x is given to us, dy by dx, that is y dash x is the first order derivative. Dy by dx is given to us as x minus y square. So our f of xy is now x minus y square, where x is the independent variable, y is the dependent variable. Since this is an initial value problem, the value of the ordinary differential equation at the initial point is given to us. This initial point is 0. That is, the value of x is 0. And what is the value of y? The value of y at x equal to 0 is equal to 1. Hence, we can say that at the initial point x1, y1, x1 is equal to 0 and y1 is equal to 1. Using this Taylor series expansion method, we now need to find out the value of the ordinary differential equation at x equal to 0.1. We have been given the value of the ordinary differential equation at x equal to 0. The next consecutive point is x equal to 0.1. Now let us have a look at the differential equation. Y dash or dy by dx is equal to x minus y square. Taylor series expansion makes use of first order, second order, third order, fourth order, and so many multiple order derivatives. But they are all ordinary derivatives. So the first and foremost activity we need to perform is to find out the values of the first order, second order, third order, and so on, the values of the derivatives. Since dy by dx is given to us, that is the first order derivative, which is x minus y square. On differentiating dy by dx with respect to x, we get the second order derivative, that is